Hey there, this is the lecture for section 5.4, the other trigonometric functions. All right, in section 5.3, we talked about the definition of the sine and the cosine. Let's just review that quickly. The sine of some angle theta is equal to y over the radius when we consider a triangle inside a circle that's made where the hypotenuse and the radius of the circle, hypotenuse, I'm sorry, of the triangle is the radius of that circle. All right, so the angle would be theta, right? The terminal side of that angle has a terminal point that has some x coordinate and some y coordinate, right? And then the radius of the circle has a measure. All right, so the definition for the sine of angle theta is this y coordinate of the terminal point divided by the radius, right? So for the unit circle, then, for the unit circle where a radius is 1, then the sine is equal to the y coordinate. Here, let's see, let me write that better. The sine is the y coordinate when the radius equals 1 on a unit circle. Okay, and then the definition for the cosine of theta is x over r, where x is the x coordinate of the terminal point and r is the radius of the circle. Okay, and then in the unit circle, when r equals 1, that x coordinate is the cosine of that angle theta, right? When r equals 1. All right, so there's a very, very brief summary of all the things we talked about, and or not all the things, but the definition anyway for the sine and the cosine. Now in this section, we're going to take a look at the remaining 4 trig functions as well as trigonometric identities. All right, so the remaining 4 functions, sorry about that, touching all the wrong things here. What can I touch? All right, the remaining 4 functions are the tangent, which is defined as y over x, right? Where y is the y coordinate of that terminal point of the angle theta, and x is the x coordinate. All right, the secant is r over x, that's the radius over that x coordinate, right? Or we can also think about that as the length of that the length of that horizontal leg of the triangle, right? The cosecant is defined as r over y, the radius over the y coordinate, or the length of the vertical leg on the triangle. All right, and then the cotangent is defined as x over y. All right, so here are the ratio definitions for these 4 remaining trig functions, but we also have some identities which we sometimes use as in place of the ratio definitions. Is it doing that? Where are we here? It just took my whole page away. Huh. I think I accidentally deleted it. Well, let me just insert a page here and type them in. Did it move it somewhere? Let me just put those identities back in. Or, you know, it might be better. Let's do this. Let me just close this and bring it back up again. And then my page will be back if it'll reopen. Here it comes. Okay, let's scroll down here to 5.4. All right, there's our identity page. It's back. All right, so these are probably the 4 most basic identities. We call these the fundamental identities, and they are on that formula sheet that's available under class information, the class information folder in Blackboard. All right, so the tangent identity it says that the tangent can be defined as the sine of theta over the cosine of theta. All right, I like to think about this as the identity definition for the tangent. All right, and it's easy to remember these because in the unit circle, the sine is the y coordinate, right? And the cosine is the x coordinate of that terminal point, right? The secant is defined as 1 over the cosine of theta, right? And the ratio definition for the secant is the radius over x, right? In the unit circle, the radius is 1 and the cosine is x. Okay, the cosecant is defined as 1 over the sine of theta, and its ratio definition is the radius over y, right? So the ratio definitions and these identity definitions are not that hard to remember, right? Because x always correlates to the cosine, y always correlates to the sine. If it's the unit circle, x is the cosine and y is the sine. All right. And the last identity we have down here is for the cotangent of theta. The cotangent, one identity is that the cotangent is equal to 1 over the tangent, right? Or we could also say that the cotangent is equal to the cosine over the sine, right? And recall that the ratio definition for the cotangent is x over y. All right, so we have different ways to think about these remaining trig functions. They all relate back to the sine and the cosine. Okay, so let's look at some examples of working with these trig functions. Say we have an angle, theta, and the measure of that angle is negative pi over 4. All right, let's see if we can find the exact value of all 6 trig functions for that angle theta. All right, now be careful when you see exact value. Know that you want to use values from the unit circle or you want to use values as ratios. You don't want to go to your calculator, right? Your calculator can give you repeating decimal, which at some point is going to have to be rounded or truncated, right? And it won't be an exact value, all right? So your calculator is no good when you see this word exact. And that's what we've got here. So here's where we begin with these. Always, when dealing with circle-based trigonometry, draw a circle so you have something to refer to. Draw a circle sitting on the origin, right, of the Cartesian plane, and then sketch in where that angle might fall. Oops. Okay, so pi over, negative pi over 4, that's a negative angle. Pi over 4, let's see, this is pi over 2 up here and pi over here, right? This down here would be 3 pi over 2 all the way around the unit circle in the positive direction, right, counterclockwise. It would stop over here at 2 pi, which is the same as 0, right? So we start over again. Well, positive pi over 4 is going to be halfway in between 0 and pi over 2 up here. Well, negative pi over 4 means instead of going counterclockwise around the unit circle, we're going to go clockwise around the unit circle. We always start at 0, but we're going to go clockwise. So negative pi over 4 is going to fall right here. And there is our angle theta. All right, this is important to draw this sketch so that you can note what quadrant your angle is in. This angle is over here in quadrant 4. And in quadrant 4, we know x's are always going to be positive, right? But y's are always going to be negative. Okay, so what quadrant we're in is what mandates whether our trig function is going to be positive or negative, right? The cosine relates to the x coordinate. So over here in quadrant 4, we have positive cosines, and the sine relates to the y coordinate. Over here, we have negative sines in quadrant 4. All right, so we need to find the sine of negative pi over 4. Well, there it is. Now, we need an exact value, so let's look at the unit circle to find that exact value. So let's see, I think I've got one right up here we can glance at real quick. Negative pi over 4 is going to be right here. Okay, that's going to be the same as positive 7 pi over 4. Here's our angle. The x and y coordinates are right here. We see that x is square root 2 over 2, and y is negative square root 2 over 2. All right, knowing those x and y coordinates, and if I wanted to, I could even label them here. I think I will. The x is positive square root 2 over 2. It's hardly legible. Let's try that again. Positive square root 2 over 2. The y is negative square root 2 over 2. All right, there's my x and y coordinates. So I have an angle measure. Let's just say this is the unit circle. It's a radius 1. Well, the sine and the cosine are easy then. The sine and the cosine are simply the x and y coordinates of the terminal point. Okay, so the sine is the y. That'll be negative square root 2 over 2. The cosine is the x. That'll be positive square root 2 over 2. All right. So the tangent, we can think about the tangent in terms of its identity definition. Its identity definition says it's the sine of theta over the cosine of theta, or we can think about it as its ratio definition. As its ratio definition, it's y over x. All right. Well, it doesn't really matter in this case for this tangent how I deal with it, since the sine is y and the cosine is x. So the value of the tangent of theta, since y, or the sine, is negative square root 2 over 2, my numerator is going to be negative square root 2 over 2, and my denominator is going to be positive square root 2 over 2, right? Which, when that simplifies, is simply negative 1. All right. Now to find the cosecant, well, two ways to do that, right? Its identity definition is 1 over the sine of theta, and its ratio definition is the radius over y, right? So I can do this either way. My radius is, of course, 1. So my cosecant is 1 over the sine. That's going to be 1 over negative square root 2 over 2. Okay, that's kind of ugly, so we should simplify that, right? Let's the compound fraction, let's divide that out. That's like 1 over 1 divided by negative square root 2 over 2. So if we keep the numerator, change the sign to multiplication, and flip the denominator, okay, then we see that that cosine is negative 2 over the square root of 2. Well, we can't quite leave it like that either, because we have an irrational denominator, and it's bad practice. We want to rationalize that denominator. So I'm going to multiply this by the square root of 2 over 2. Right? So then we'll have negative 2 square roots of 2 divided by square root of 2 times square root of 2 is 2. Okay? And I still shouldn't leave it just like that, should I? Because that's a fraction that can be reduced, so I should reduce it. Look, the 2's divide out. So this answer should be written as negative square root of 2. All right. Now for my open math, I don't know if it would accept this awful, ugly first version over here. I don't know if it would accept this version where there's no rationalized denominator. I'm certain it'll accept the last version of this in its correct form here. Okay. Secant is defined as 1 over the cosine of theta. Right? So that's, or its ratio definition is the radius over x. All right, well, our radius is 1, so it's going to be 1 over x, which is square root 2 over 2. You can see it from the cosine here. We can see it from the x coordinate there. Okay, go through this whole process here, and what do we end up with? Keep, change, flip, it would be 2 over square root of 2 times square root of 2 over square root of 2. So we would get 2 square roots of 2 over 2 and divide it out. Final answer here would be, oops, not negative, positive square root of 2. Okay, and then lastly, we have the cotangent. The cotangent's identity, fundamental identity, we could write this as 1 over the tangent of theta, right? Or we could write this as the cosine of theta over the sine of theta, or its ratio definition is x over y, okay? So the cotangent, let's see, which version do I want to use? Well, I think I want to use the easiest version. Look, up here I see the tangent is -1. Well, since the cotangent is 1, the tangent would be 1 over -1. It just so happens that for this particular angle, the cotangent and the tangent have the same value. All right? Okay, very, very, very important to sketch yourself a unit circle, to sketch yourself a circle whenever you're dealing with circle-based trigonometry. Draw your angles, see what quadrant you're in. That's going to tell you whether you want a positive or negative sign, you know, or whether your sine or cosine is going to be positive or negative, right? And then everything else is derived from the sine and the cosine. All right, let's look at another example here. In this one, let's say we know that the cosecant of angle theta is 9/4, and then that angle is in quadrant 2. Okay, always, always, always draw yourself a sketch. Let's see what that looks like. So there's a unit circle sitting on the origin. Okay, now we're at quadrant 2. Quadrant 1 is here. Quadrant 2 is over here. All right, so our x's will be negative and our y's will be positive. Don't have any idea where that angle is, so I'll just say maybe this is the angle. Oops, kind of a crooked one, but this is the angle. So there's our theta. Terminates over here in quadrant 2. Okay, that's an obtuse angle. All right, it has terminal points. The x is going to be something negative, right? So the x will be something negative. The y will be something positive. I don't know what it is yet, okay? But I do know that the cosine will be negative and the sine will be positive because of the quadrant that it's in. All right, so how do we go about finding all these trig functions? We know the cosecant. Well, what do we know about the cosecant? Well, the identity function for the cosecant, right? The identity function says that's 1 over the sine. Well, if the identity function, so it's 1 over the sine. If I could find the sine, well, I don't know I know the cosecant, but not the sine, right? So I could then say that one way to do this would be to say 9/4 is equal to 1 over the sine of theta, right? And that's something I can definitely solve for the sine of theta, right? I can do that with cross products, right? So that means that 9 times the sine of theta equals 1 times 4, or the sine of theta divided both sides by 9 is 4/9. Okay, well, there's one way I could find the sine. It's 4/9. How would I find the rest of these? You know, that's a little bit of a problem, isn't it? I need to know the cosine before I can find the rest of these. Well, let's see. If we take a look at that angle, let's think about its reference angle for a minute, right? The reference angle for theta, right? That's the smallest angle that's formed between the terminal side of our angle and the horizontal, right? So this right here, the double bar angle, that's our reference angle. And look, it has the same cosine and sine, right? Because cosine is the x-coordinate, sine is the y-coordinate in the unit circle. It has the same cosine and sine as our angle theta, okay? Well, if we use our reference angle, we can drop a perpendicular here and make a right triangle, right? Let me just draw it again. I'm going to blow it up, make it just a little bit bigger so I have more room to write. All right, so that's that little triangle that I just made in here. Here's our angle. This is our reference angle for theta, right? Here's our radius of the circle. The terminal point here is xy, right? Since the terminal point is xy, that means this leg, vertical leg, the vertical leg has a measure of y, and the horizontal leg has a measure of x. We know that x is going to be negative. Okay, if oops, if the cosecant of theta is 9/4, we know that the ratio definition for the cosecant of theta is the radius over y, right? Radius over y. So if 9/4 equals the radius over y, we can just say this is a triangle that's not in the unit circle anymore, right? We don't have to think about a unit circle here. We can say this is just some triangle that has a radius of 9 and a y coordinate, or this vertical leg has a length of 4. Okay, and this, since we dropped a perpendicular here, this is a right triangle. And what's the most common theorem that's used on right triangles? It's the Pythagorean theorem, right? The Pythagorean theorem, which says that leg squared plus leg squared equals hypotenuse squared, or in this case, we'll say, I'm probably going to run out of room, so let me write it over here. Let me just erase that and write it here. X squared hits one of the legs, right? So x squared plus the other leg squared, that'll be 4 squared, is going to be equal to that radius squared, 9 squared. All right, so then x squared is equal to 6, I'm sorry, x plus 16. Oh, what happened? I don't know, my computer's doing weird things to me. Oh, it blew it up is all. Let's see if we can shrink it down. This tablet is just tired. It's been overworked today. Here, let's try this. Okay, we're back. Excuse me. Okay, x squared plus 16 is equal to 81. Subtract the 16 from both sides, so x squared then is 65. Take the square root of both sides. X is going to be equal to positive or negative square root of 65. Okay, well, which one is it? Well, if it was a measure of a triangle, we would say positive, but it's not. It's got to be negative because, look, we put our triangle over here, and we're really using that leg to find our x coordinate, right? So we want negative square root of 65. Okay. Now that we know this x coordinate, it's really, a measure is square root of 65, but I'm going to keep, I don't want to lose my sign there, so I'm going to say it's negative square root of 65. The cosine then, okay, its ratio definition is the radius over x, so we can say that this is 9 over negative square root of 65, and we should rationalize that denominator. So we'll multiply by the square root of 65 over the square root of 65, and we'll have 9 square roots of 65 divided by 65, and that has to be negative, right? There's a negative in there. So there's our cosine, right? We can always do that by making a right triangle and going from there. All right, now the tangent, let's see. We can use the ratio definition for the tangent, or we could use, the identity. I'm not going to use the identity because it's going to involve a fraction over a fraction. The ratio definition is going to be easier. It's y over x, right? And y is 4, x is negative square root of 65, and we have to rationalize that again, right? So we'll multiply by the square root of 65 over the square root of 65. The tangent is going to be negative 4 square roots of 65 over 65. Okay. Now, if I could have used the identity as well, with the identity, right, it's sine of cosine, and it just would have involved a lot of manipulation. This way, a lot of algebraic manipulation. This way is just easier. Okay, I did that wrong. Cosine isn't r over x. Let me fix that. Cosine is x over r. Sorry, I went dyslexic on you just for a little bit. Cosine is x over r. So cosine is negative square root of 65 over 9. Okay, much better. Okay, now the secant, I don't want you right now. You go away, calculator. The secant, its ratio definition is the radius over x, right? So that's going to be 9 is our radius, x is negative square root 65. So let's rationalize that denominator, square root of 65 multiplied by square root of 65 over square root of 65. So this then becomes 9, negative 9 square roots of 65 over 65. Okay, negative. And then lastly, we have the cotangent. Definition for the cotangent, its ratio definition is x over y. Okay, so it'd be x, it would be negative square root of 65 over y, which is 4. All right? Okay. So this section also deals with establishing identities or proving identities, right? Or simplifying trigonometric expressions. And let's talk. Well, what is an identity? An identity is just an equation that's always true. Here's an example of an identity. It says prove that 1 plus the cotangent of alpha over the cosecant of alpha equals the sine of alpha plus the cosine of alpha. All right. So what are we supposed to do here? We're supposed to make one side equal the other side, and because we're proving it, we've got to justify each step with a reason. All right. These can be a little tricky, right? These can be a little tricky. So some tips that usually work, I wouldn't call this a procedure to follow, right? But a guideline, more of a guideline, is start by working on the side that looks more complicated. You never ever want to work on both sides because you're writing a proof here. You're not solving an equation. The assumption is that it is equal, and you're not trying to solve for anything, so you don't want to work on both sides of the equation. You only want to work on one side of the equation, and you're going to do things like make substitutions or do some algebraic operations on it to try to make one side look exactly like the other side. All right. So we start on the side that looks more complicated because it's much, much, much easier to simplify than it is to start with something more simple and expand it to something more complex. So we always start on the side that looks more complicated, okay? And then we try, one technique that often works is to rewrite all the terms on that side so that they are expressions of the sine and the cosine, right? Or you can think about switching everything over to sine and cosine. So we use the fundamental identities to rewrite non-sine and cosine trig functions as sine and cosine expressions, all right? Sometimes we have to factor to get to where we want to go. You know, other times we may need to add or subtract fractions. So multiplying by a useful one can help. In other words, establish a common denominator so I can add or subtract the fractions. All right. Sometimes the Pythagorean identity can help us. Remember the Pythagorean identity? Sine squared plus cosine squared equals 1. Okay. And then once you've got an established identity, you can use it in the future. You can continue to use that new identity. All right, so let's see if we can prove a couple of these identities. Let's look at this first one. All right, we want to start on the side that looks more complicated, and I think the left side looks more complicated. The right side just has a sine and a cosine in it. The left side, it's got fraction, it's got a non-sine cosine trig function, a cotangent, a cosecant, a constant. I think I want to work on the left side. All right, so you know, where do I go from here? Well, I don't really see a relationship between them offhand, but I do know that to make this left side look like the right side, it has to have only sines and cosines in it. So I think that second tip here of switching all the terms to sine and cosine is what I want to do. Okay, so I want to rewrite the terms on the left so that they're an expression of sine or cosine. All right, so we're going to work on the left. So we're going to say 1 plus, and instead of cotangent, I'm going to use the fundamental identity. The cotangent is equal to the cosine over the sine. Okay, so I'm going to substitute in the cosine of theta over the sine of theta for the cotangent. And then what I always like to do in my proofs is over here, I say why, or I give the justification for what I've just done. The justification here is that the cotangent equals the cosine over the sine, right? It's the fundamental identity. Okay, and that's going to be over, now my denominator is a cosecant. Well, the fundamental identity for the cosecant says that's equal to 1 over the sine. Okay, so that's my reason. I need to write another reason here. The cosecant, oops, I'm using theta and I'm supposed to be using alpha. Let's switch to alpha. The cosecant of alpha is equal to 1 over the sine of alpha. All right, so there's my justification. Let's switch those thetas to alpha. Okay, now what? Now where do we go from here? Yikes. Well, at least that doesn't look anything like that, does it? Well, I'm going to need to rearrange some things. I got a compound fraction. That's kind of ugly. I also have 2 terms in the numerator. How about if we add those two terms in the numerator? Let's try adding the terms in the numerator. All right, so let's rewrite 1 with a denominator of sine, right? So 1, I could say that 1 is equal to the sine over the sine, right? I've got some thetas left here. Let me get those to be alphas. Okay, and I can make that substitution there. All right, so I'll rewrite this then as the sine of alpha over the sine of alpha plus the cosine of alpha over the sine of alpha. Then I'll be able to add the numerators. I just copy down that denominator, 1 over the sine of alpha. Okay, so when I add them together, then I'll have the sine of alpha plus the cosine of alpha over the sine of alpha, all of it over 1 over the sine of alpha. And my reason that I can do that is adding fractions. I'm just adding the fractions. There's my justification. Okay. Now I've got this compound fraction. He's ugly. Let's break that up. We'll do keep, change, flip on that, or we'll divide those fractions, right? So we'll rewrite this as the sine of alpha plus the cosine of alpha over the sine of alpha. That's the numerator. Then we're going to change this division to multiplication and flip that denominator. Okay, so that's the sine of alpha over 1. All right, and the reason we can do that is divide fractions. That's how we divide fractions. All right, and there's my justification. Now look at this. When we multiply fractions, we just multiply the numerators, right, and the denominators. Multiply straight across. It's like they're one big fraction. So we can divide out that sine alpha, right, and we're left with what we want. I've got a sine alpha plus a cosine alpha, all right? And my justification for that is simply, we'll just say simplify. Okay? Let's try another one. Look at these. All right, we've got we've got 2 identities here that we want to prove. 1 plus the tangent squared equals the secant squared, and the cotangent squared plus 1 equals cosecant squared. By the way, these are just alternate forms of the Pythagorean identity, and I think these identities they're written on your formula sheet. All right, this is actually not going to be enough room. I'm writing too big on my tablet, so let me do something here. Let's just copy that. Copy, paste, there. Just need twice. Okay, and I'll just delete out what I don't want up here. Maybe. That's not working. There we go. Okay, so where do I want to start? Well, the left side looks a little more complicated than the right, so I think I'll start over here on the left. Okay, and I think I'll go with converting to sine and cosine again. That seemed to work well last time. Let's see if it works well again, right? So I'll rewrite that 1 plus the tangent. Well, actually, I have to I have to factor that tangent first, don't I? I don't have any identities that deal with the tangent squared of theta. So the first thing I'm going to have to do is I'm going to have to write this as the tangent of theta times the tangent of theta, right? The justification for that is just that I'm going to have to factor that first. I do have an identity for the tangent of theta, just not tangent squared of theta, all right? So now I can convert to sine and cosine. Tangent of theta is the sine of theta over the cosine of theta. Okay, and my justification for that is the fundamental tangent identity, which tangent of theta is equal to the sine over the cosine. All right, let's simplify that. So we'll write it as 1 plus sine squared theta over cosine squared theta. Simplify or multiply? I don't know. I'll say multiply, I guess, since that's what we did. Okay, now what? Well, I only have one term on the right, and there's two terms on the left. I need this left to look like the right, so I need to combine these terms. Well, I've made that tangent squared into a fraction now, so that means I could change that 1 to cosine squared over cosine squared, and then I could add them. All right, so I'll rewrite that 1 as cosine squared theta over cosine squared theta. Oops, that's supposed to be cosine down there. Okay, my justification here is simple. 1 equals cosine squared over cosine squared. All right, now I can add them together. And write them as cosine squared theta plus sine squared theta over cosine squared theta. Okay. So that's just add fractions. Okay, now what? I need to get to secant squared. Oh, I see it. Do you see it? The secant identity it says that the secant is 1 over the cosine, right? So the secant squared must be 1 over cosine squared. We're getting there, but we're going to have to write each step because this is actually a proof, right? Well, how can I get that numerator to be a 1? The Pythagorean identity, right? Remember that? Sine squared plus cosine squared, or cosine squared plus sine squared, since addition is commutative. Sine squared plus cosine squared equals 1. So I can rewrite that whole numerator as just 1 over cosine squared. Now I don't have an identity for cosine squared, so I'm going to have to factor this again. This would become 1 over cosine times 1 over cosine factor. All right, and then I can now substitute in secant is equal to 1 over the cosine. Okay, we'll make that substitution. Secant of theta times the secant of theta, and then we just multiply them out. And we have proven our identity. My justification there is simply multiply. All right. Let's look at that second one. It's very similar to this one. Cotangent squared. Here, let's delete out what we don't want. We don't need that. Get him going. Oops. I don't want to take it all away. I do, let's see. I don't want this guy. We just solved him. So let's take him away. All right. prove cotangent squared of theta plus 1 is cosecant squared of theta. Okay, this one is a very similar proof, right? Because cosecant squared is 1 over sine, and cotangent is cosine over sine. So I think I can use that same strategy. All right, let's factor it first. Cotangent of theta times cotangent of theta plus 1. We'll do that because it's a factoring. Now let's substitute for the cotangent. Let's substitute the cosine theta over the cosine of theta. I'm sorry, over the sine of theta. So we have cosine theta divided by sine theta times cosine theta divided by sine theta, right? And then plus the 1. Now let's multiply to simplify. Cosine squared theta over sine squared theta plus 1. All right, let's see if we can combine those. We only want one term. So I can multiply that 1 by sine squared over sine squared, right? So 1 is equal to sine squared theta over sine squared theta. So we now have cosine squared theta over sine squared theta plus sine squared theta over sine squared theta, and we can add them. Cosine squared theta plus sine squared theta over sine squared theta. Okay, our justification here, add fractions. Okay, now we can use the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. So 1 over, I'll substitute 1 in for the cosine squared plus sine squared. And we have 1 over sine squared theta. Okay, we have no identities for squared sine squared theta, so let's factor it. And now make a substitution. The cosecant is equal to 1 over the sine. So we can call this the cosecant theta times the cosecant of theta, and then when we multiply that out, we've completed our proof. That will equal the cosecant squared of theta. Justification of the last step is just multiply. Okay, that ends the lecture for section 5.4, the other trigonometric functions.